Okay, Coulomb's law. Let me go ahead and say the idea of a law. I mean, it's okay to use that terminology. It's not like you have to obey this. So I just want to make sure that we understand the nature of science. Really, you could say this is Coulomb's model for the interaction between charges. That's better. I like model. I'm a big model fan. So let's just jump into it. Suppose I have two charges, and Coulomb did this. So really what happened, people had these electric charges and they could rub things and charge it up, just like your socks coming out of the dryer, they get charged. And there was an idea that, hey, maybe this looks like this. I'm going to write it the correct way. That's not the way they wrote it, though. Maybe it's the inverse square law, just like gravity has an inverse square law. Maybe it's also an inverse square law. So what Cavendish did was to take two charges that are the same value, and you could get two spheres, and if they're in contact, they can end up with the same charge. And then he would use what's called a torsion balance. So this is one of the ways it could look. If it's viewing from this above, this could be fixed. This could be locked on this bar that's suspended from a string. Actually, it needs a counterweight too. And then the electrical force between these would cause this wire to bend, and the amount of bending is proportional to the torsion force. This is called a torsion balance. And then you can measure, they have the same charge. You can measure this distance. I'll just call it R for right now. And then you plot force as a function of distance, and you get something like this. Force, distance, and you get this. And then the question is, okay, now is that 1 over r squared? And you can see that it is. And in the end, we have the following format for the force between two electric charges. And we call this the Coulomb force. Fc, it's going to be equal to K, Q1, Q2 over the magnitude of r, where this is the vector r from one to the other. Magnitude of r squared times r hat. Oh, that's not a unit vector. That's like that. Okay. And in this case, K is equal to 9 times 10 to the negative ninth newtons meter squared per coulomb squared. And coulomb is a unit of charge. And that's it. So there's actually another form too. A couple important points, differences between these two. They look very similar, right? They're both vectors. They both have a constant. They both have a product of two terms. They both depend on the distance squared. So that's very similar. But the big difference is this minus sign. I'll circle it right there in red. And this one doesn't have that. And that's because if I determine the vector from these two, and they're both positively charged, they're going to repel. They're going to be pushing apart. So the force will be in the same direction as r. That's why this is positive here. If, however, I could have this. I could have a negative charge, in which case one of these would have a negative value, and it'd be an attractive force. So over here, there's no negative mass that we know of. Okay, so there's only an attractive force. In this case, we could have attractive or repulsive force. Another important thing, you may think, oh, well, this is such a weak force. That's true. But remember this gravitational constant G. G equals 6.67 times 10 to the negative 11th. This is, that's times 10 to the ninth. So it's a big difference. Big difference, not negative 9. Okay. So there's a big difference between these two forces constants. Of course, it's hard to compare apples and oranges. Charge as a mass aren't really the same thing, but just orders of magnitude. Generally, we're going to see it's possible to see greater electrical forces between charges than you would see gravitational forces between masses. One more thing, this constant K, sometimes we write this as 1 over 4 pi epsilon naught. And so 4 pi, Epsilon naught's just a free space, a permittivity of free space. It's not super important, but just in case you see that. Okay, so that's Coulomb's law. We're going to use this now to do a fun, it's going to be fun, it's got to be fun, physics problem.